So last week we have learned chapter 1 and chapter 2, which is the introduction to the microprocessor and also the architecture of the microprocessor, particularly for the ARM microprocessor that we will use in this course. Right? So for this chapter, we will learn a more interesting uh, part in this course where after we learn the architecture, now we want to use to program the microprocessor based on the resources that we have, which is um, the hardware architecture. All right. So in order to program the microprocessor, we need to understand or know the hardware, the internal hardware of the microprocessor. What are the resources that we have, especially the internal register, the memory organization, and the programmer model is very important for that purpose. Uh, in this chapter, what we will look at is this, yeah. So the first one, we will look at the development flow, where, for example, we want to start or create the project based or using the microprocessor or microcontroller as a brain of our system. So how we start to develop the things from the start point to the end. All right, what is the flow that we need to follow. And later we will look at data representation, how we represent a data in microprocessor, how the microprocessor interpret the data, right? So because we want to process the data and the data is from outside the microprocessor, from human, from the sensor, right? So we need to understand how the microprocessor interpret the data, read the data, and write the data. And after that, we will look at what is called the instruction set in detail. Right. So in the previous chapter, you have been introduced to instruction set IS architecture, right? So what is instruction set? Instruction set is actually a signal, a command that we use to instruct the microprocessor to perform tasks. And when we have a series of instruction, all right, for example, the first instruction is this, second is this, third, and so on and so forth. So we can get the program, all right, where the microprocessor will follow the instruction one by one and perform the function that we want the microprocessor to do. And after we learn all the instruction set, not all actually, because we have a very uh, large number of instruction. We will learn the most important one, the commonly used instruction set, and after we learn this, we will write the program. Right. So the program for microcontroller or microprocessor can be in form of two languages. First one is the low-level language, which is the assembly language, where we use instruction set, a set of instruction to write the program for the microprocessor. That is called the assembly language. And we can use also the high-level language, especially the C or C++ language, or any other high-level language, for example, Python, Java, right? So that are the high level programming language. So we will learn both. The low level here means that the assembly language, the instruction set, means that the instruction that directly represent the hardware of the microprocessor, and the high level language, which is uh, the language that designed uh, to help programmer uh, write more complex program, because writing in a program in assembly language is actually difficult and very hard, very time consuming. So the better way is to use the high level language, C or C++ or any other languages. Okay, so first thing we want to look at is the development flow of the um, developing a microprocessor project. Particularly in our case is using a microprocessor. So we can have two file for programming. All right, the first one is the assembly file, assembly language. We will look at this shortly, and we have also C or C++ or any other languages actually, and use the compiler. So the compiler is the program running sitting on your PC that is used to convert this source file into a machine language that is understood by microprocessor, right? We call it compiler. And this compiler will change or convert the source file into what we call an object file, right? Whether you program or write a program in assembly or C, both will be converted to object file, right? Object file, and the compiler also has what we call a linker. So this linker is actually to uh, to combine all the object file that you have to create what we call the executable file, the file that can be executed by your microprocessor. All right, so uh, this one, the binary image file, or .bin file, and also another file is called disassemble file, where this is not executed by the microprocessor, but this is for programmer for to see what is the or as a reference for the programmer. Okay, so that is the flow. The flow. So this file will be sitting or will be programmed into the microprocessor. All right, and the microprocessor will run this program to perform the task that we want to do, right, based on what we write in the program. Okay, so this is the flow that we go through in developing the microprocessor project in this course. All right, now look at the data representation, how we use the data or represent the data in the microprocessor. All right, basically we have or we represent the data in byte format, or 8-bit, or 16-bit, we call it half word, and word, 32-bit, and some microprocessor we have 64-bit, we call long word, right? And also we have the signed and unsigned number, right? So unsigned number is number from 0 to any positive number based on the size of our microprocessor, right? So for example, if our microprocessor is 8-bit, so the maximum unsigned number should be 255, right? FF, right? And minimum is 0. And for signed number, the computer or microprocessor will use what we call the two's complement, uh, for represent the negative number. So why we use two's complement? We have learned this already actually in digital design, right? Because we want to do arithmetic operation, right? And for adding number, positive number is okay, but for subtract, we need to use adder also. But to use adder for subtraction, we need to use the two's complement. So you need to the process is learned already last previous semester. So for sine number, the for example, is our microprocessor is 8-bit. So the smallest number that we can put in our microprocessor is -1 to 7, and -1 to 8, and largest positive side is +1 to 7, right? Uh, uh, okay, so that is the data representation, and we actually learned this already in data design. And now we will look at instruction set. So there are groups of instruction set in a microprocessor, and this is the main group that we have, right? So the first group is moving that data within the processor. Means that last week we have learned the internal architecture of the microprocessor. We have learned the programmer model. We know that in our microprocessor we have internal register, and the general purpose register we have R0 until R15 for the register that we can use, and for general purpose one is actually R0 to R12, right? The others is for special purpose. So what is the instruction that we can use to move the data? For example, we want to send the data or copy the data from R0 go to R1, or R1 go to R2, and so on. So what are the instructions that we can use for that case? And next we will look at what is called memory access instruction. So how we get the data from the memory, how we send the data to the memory, right? So this will be a memory access instruction. And the arithmetic operation, which is very important in microprocessor. So how we perform arithmetic operation on the data that we have, right? We will look at what are the instructions that are available for this operation. And next we will look at logic operation, right? Logic is very important in microprocessor, right? Remember we have ALU, arithmetic, and logic unit. So that unit will perform these two operations, arithmetic and logic. And also we have the shift and rotate operation. Shift, we learn in digital design as well how to shift the data, and shift the data is very important in digital, especially in microprocessor. And the last part is the what we call the program flow control. Because we write the program uh, most of the time is not a linear program. I mean, from line number one, line number two in sequence. Sometimes we will need to have a program that is not running in sequence. For example, at this point, we need to test whether the number is equal. If equal, what to do, if not equal, what to do. All right, so we need what we call a program flow control to force the microprocessor uh, to jump to other location of the program. All right, that is called the program flow control. So these are the main groups of the instruction set that we need to learn in this course. Now look at the first instruction, moving data in within the processor, right? So the first instruction and very important instruction is the move instruction. So if you learn any microprocessor that we have today, whether you use ARM, whether you use Intel, whether you use microcontroller, the Arduino, the ARM microcontroller, or any other microprocessor that we have today, this is the instruction that each microprocessor must have, right? Move. So the format is this move. This is destination register. All right. So destination first before the source. Source is the the source of the data that we want to get. So we will move the data from the source to the destination. For example, uh, this is destination. This is source. For example, we want to move the data from R0 to R2. So this is R0 and this is R2. And remember in our microprocessor, the ARM microprocessor that we learned, the size is 32-bit. Means that the size of R0 here is 32-bit and this is 32-bit data in hexadecimal, 8 digit. So this 8 digit hex value, we want to move to R2. Right? So this is the instruction. Very easy. And the operation is 32-bit. Means that if you want to move data, you will move all the 32-bit data into the new register. You cannot move only one byte or half word. All right. So you need to move word of data. Some microprocessor you have uh, the the feature to move byte, only one byte of data from R0 to R2, for example, or half word data to R2. Some of the microprocessor, especially the CISC one, because CISC we learned already, they have many variant of instruction, and because of that, the size of the microprocessor and the complexity is bigger, is more complex. So for RISC or ARM, when you want to move, all 32-bit will go to R2. And when we run this instruction, the data will go to R2. And when we say move in microprocessor, this is actually copy. Copy means that the previous register here, R0, is still this. We just have a new value in R2. All right. Copy, And why is that? Why is copy? We also know this because of in digital, when we move the data means that we read the data. So the data is still in the register unless you clear the register. But that is not necessary, unnecessary for to do that. All right. When we want to clear this, we need a new instruction, or we just put 0 in the register. All right. Very easy. Now the next instruction is to put number, insert number in from the outside. Before this, the number is inside the microprocessor already. We want to move the data within the microprocessor. Now, let's say the number is from outside, means that from programmer, we want to put any number into a register. We as a programmer, for example, we want to put 5 in register R0. What to do? So the instruction is move also, but called move immediate instruction. Then we call it move immediate. So this is destination register, and this is called immediate value, the value that we want to move into the register. And the format is this. We have the hash before the number that we want to move to. For example, we want to move number 9 into R0, right? So this is the instruction, and when we execute this, we will have 9 in R0, right? And the size of value, this immediate value is 8-bit, right? And for new microprocessor nowadays, we can have up to 16-bit, right? But no more than that. Okay, we will see the reason later on why the number here is cannot be more than 16. All right. For example, if you want to move 32-bit number into the register using one instruction, you cannot do that, right? So if you cannot do that, how to do? Okay, after this. And if we have this instruction, for example, move R0, all right, this is immediate, -9, number negative, negative number. So what we will have in the register is this. This is -9 in 2's complement, 32-bit, negative number. -9 is here. This is the variant of move immediate instruction where we can have 16-bit immediate value. So the name is move W or move Y. Move W, same thing, destination and the value. The value here can is 16-bit, all right? 16-bit immediate value. For example, this is 16-bit data. We want to put in R0, so we can have this after we execute this instruction, right? Very straightforward. And this is another one, move T or move top. Yeah. So this is the way of insert a 32-bit number into the microprocessor, right? So first is we use move W, 16-bit, and another one we use move T, top, means that we move another 16-bit value into the top half word of the register. So move top means that you move another 16-bit or move 16-bit value into the top half word of the register. So for example, if we have this instruction, move T R0, yeah, A, B, C, D. So what we have is, if initially R0 we have 0, 0, 0, 0, 1, 2, 3, 4. When we execute move top R0, A, B, C, D, we will have A, B, C, D, 1, 2, 3, 4. Right? So that is move top. Means that if we want to move a 32-bit number into a register, we need to use two instructions, right? The first one is to move W, for the first 16-bit or first half word into the lower half word of the register. For example, this, this, we will have 1, 2, 3, 4 in R0. And when we move top, we will have another 16-bit in R0. So that is the way to have a 32-bit number in the register. And the last move instruction is move immediate complement, right, or MVN. Okay. So this again, this destination register, and this is the value, right? So for example, when we move R0, move MVN, move negate or move complement, means that we move the first complement of 1 into R0. Yeah. So what is first complement of 1? This is first complement of 1, 32-bit. All right. So when you have a 32-bit number. So for example, if you have a 8-bit number, right? So 1 in 8-bit is 0, 0, 0, 0, 0, 0, 0, 1. And when you complement this, you will have 1, 1, 1, 1, 1, 1, 1, 0, or this is F, E. But this is 8-bit, right? So if you have 32-bit, so you will have this when you use MVN. Okay, so that will be the first set or first group of the instruction, the move instruction. All right, so you have flexibility to, or features to move the data within the processor, and you also have the flexibility to have to insert the data from the outside into the microprocessor. We call it move immediate instruction. All right. So the next one is the load and store instruction, or memory access. So remember, in the previous lecture, in the previous class, we have learned the ISA, and we know that the RISC, and particularly this microprocessor, the ARM microprocessor, use the load and store instruction. Load and store instruction to access the memory. All right, load is to read from the memory, and store is to write into the memory. Okay, so now we will look at what is the instruction that is used for load and for store. Right. So again, this is the instruction. The store is str destination, and this is the this is the source in this case for the store, and this is the destination. Right. This is opposite from the previous one for the move, because the move, this one is destination and this one is the uh, the source. But for the store, only for the store instruction, this is the source and this is the destination, and destination is in bracket like this, where the address of the memory that you want to access is inside this register. Right. But for load, for load, this is the source, this is the destination, and the art is for load. Okay, now look at the first example, the store instruction. Right. For example, we want to store the data in art1 into the memory pointed by the value, the address in art0. So art0, we have this. So this is the address in the memory. All right, and this is the data in art1. We have 1, 2, 3, 4, 5, 6, 7, 8. So we want to store in this in the memory, means that this is in memory. So we want to store here. But remember that the data is 8-bit, and STR, the data is 32-bit, and STR, this is 32-bit operation, means that when we execute this instruction, all 32-bit data will go to 20000000. So the issue or the problem is that this location in memory is 8-bit. All right, but our data is 32-bit. So what happened when we transfer or store the data, 32-bit data, into the memory location, which is 8-bit? So what happened is this: it will move all the data from this into the memory, starting from address 20000000 and until this. So it will need 4 memory location in order to store this 32-bit data, because this 32-bit data, you need to have how many byte? You need to have 4 byte, right? 1, 2, 3, 4. 4 byte. So this 4 byte is the data from here. So you need 4 location, 4 memory location from location number 2000, 1, 2 until 3. And you see how it is stored. It will store the first, the least significant byte first, 78, followed by the next 56, 56, 34, 34, 12, 12 is the last to be stored in the memory, right? And this is called the effective address, R0. In the bracket is the effective address. Effective address means that the address that we want to access, right? So in this case is this. So this is the explanation of how the data, this 32-bit data is stored in the memory. So in ARM microprocessor, we call this storing mode as little endian mode. All right. So there are two type of storing data in memory. First is little endian, and the second one is the big endian mode. So some of the microprocessor using big endian, some of the microprocessor using little endian, but the ARM microprocessor using little endian. So what is little endian? Little endian is this, the one that I explained just now, where the least significant byte is stored first. Is stored first here, 78, followed by the next 56, 34, and 12. But for the big endian mode, all right, the data is start from MSB, MS most significant byte, which is 12. So 12 here, followed by 3, 4, 5, 6, 7, 8. That is big endian. But in our case, we use little endian, remember? Right, so when you learn other type of microprocessor, when you see the big endian, so you know already that the method of storing the data is this, 1, 2, 3, 4, but little endian like this, right? So that is the differences. So there are two type of storing mode only, big and little endian, right? So depend on the microprocessor that we use. So the ARM that we use using the little endian. All right, so that will be storing 32 bit of data into the memory, but we have the option to store only 16 bit 16 bit data in the memory. So for example, this is the data in art1 also. Now we don't want to move all 32 bit into the memory. We only want to move half word, the lowest half word of art1 into the memory location in art0. So here, so this is the instruction start h. H means half word. So now art1, if we have art1 is this, and effective address is in art0, which is 20000000, means that here, means that after we execute this instruction, we only have this two memory location that is need to store this data, and this is what we get, 7856, 7856, little endian, right? So this is store half word, and we also can store 1 byte from the register into the memory. So the instruction is str b, byte. So again, same thing here, right? Effective address is to this. So now 78 will go to the memory. 78 here, right? So that will be the store. What about the load? Load means that we read from the memory into the microprocessor or into the register. So for example, we want to read data, get the data from this memory location, the effective address in R0. So here, this is the address, and here the size is 32-bit. LDR is 32-bit. So LDR data 32-bit starting from 20000. This 0 here, which we have AA, BB, CC, DD. All right. So when we move the data from here to here, we will have, remember, little endian. So DD will go first. DD, CC, BB, AA. DD, CC, BB, AA here. Right. We also have the option to have to use 16-bit to transfer 16-bit or half word. So again, the instruction is LD art H. So now, if half word, the data must be these two. So we can have BBAA when we execute the instruction BBAA. And last one, we can have byte. Byte. So if byte, only this AA will go to R2. All right, very easy. Okay. Now we will look at the extension or variant of load and store instruction. We have option to use what we call the offset in the addressing mode, right? So what is offset? The offset is another information that we will use to generate the effective address in order to get our data. All right. So this is the format. All right. Uh, Similar to the previous one, the only difference is that the address that we want to access have this offset, right? So the offset size is this must be from -255 to 40595. So let's see what is the offset. So for example, if we write the code, the instruction like this, store B means that we store 1 byte from art1, all right, means that this byte, right, 78 here, into the memory location that is defined by this. So our task is to get the effective address. All right, so first the information is from art0, so should be art0, this number. And what is this? This is called offset, and this offset this offset must be added into this the content of art0. So the effective address is this value plus the offset, so we get this value. Means that the address, the actual address that we want to access is this, not this. All right, the address in the register plus the offset, this one. So the value from here will go to here, 78. So that is the offset, right? 78 will go to this. And we have another addressing mode. We call it post index. Post index addressing mode. We have offset also in post index, but the offset is outside the square bracket here. And the value of the offset must be between -255 to 255, right? And what is offset? What is offset, or how to use the offset in this instruction? So for example, we have this instruction. Again, byte art1 means that this value, art0. So in this case, the effective address is this, art0, means that the data here will go to the effective address, which is this one. So we'll go to 78. But the difference from the previous instruction is that the value inside art0 is updated to a new value based on this offset. Means that the value here in art0 before is we have this. After we run the instruction, this is this. Means that this value is added in with the offset, and we get the new art0. In the previous instruction, for example, this one, the value of the address here is not updated. All right. Although we get the address here, effective address is this, but after we execute the instruction, this one remain this value. Remain the same. The only difference is that the address that we want to look at. All right. So this is internally, but in the register, nothing changed. But for this one, post index, right, we store the data first and we update the address, the address here in art0, right? So here, this is called post index. All right, art0 is updated. And we have another one is called pre-index. The previous one is post index, and the next is pre-index addressing. So what is pre-index? So this is the format. So the offset is here inside, and we have this symbol after uh, the bracket, and the size of the offset must be between -255 to 255. Again, this one, yeah, pre-index means that if the offset is inside the bracket, means that we need to get the effective address by adding these two number, right? So we update the R0 first, and this will be the effective address, and the data will go to this 78 based on the updated value of R0. All right. For post index, remember previously the effective address is this. We send the data to this and we update. Right. For the pre-index, we update first, and this will be the effective address, and we move the data. That is pre-index. Yeah. Right. There are many options or many features. So all are very useful in writing the program later on when we manipulate the data in the memory. All right, so that will be the first two group of the instruction. First one is moving data around the memory, around the register, and the second one is moving the data from memory to register and from register to memory. Later we will look at the logic and arithmetic instruction, and before that I will show you how to use the software where before this yesterday I asked you to download from the website, right? Maybe you can use do this together, yeah, to write a simple program and see what happened when we simulate the program using the this software that we have. Okay, so the software is the Kill UVision 5. Try to launch the software. Okay, so when you first launch the Kill UVision 5, so this is the interface. I think my one is not the latest one. This is the previous version. So maybe if you download yesterday, you will get the latest one, right? So this is 2018, right? But the compiler is keep updated. Keep updated means that if we online, so we will receive the latest update, right? So this is actually not too much different. So this is the interface where we can write our program here and we can simulate our design, and also we can actually connect the hardware, the microprocessor, to our computer through USB, and we can do the debugging, and also we can program the microprocessor using this kill. So how to start a new project? So for example, we want to do a very simple program here to demonstrate what we have learned just now, which is the move the data into the register or data between the register, and also send the data into memory, right? How to do that here? Okay, so if you have your computer, maybe you can have your kill open also. So first thing, what you need to do is you go to project. You can have this new vision or micro vision. So you need to have a new folder. For example, I call this okay, and the project file, the project name is maybe we can use the same name as our folder. So make sure that you, if you have a new project, make sure that you have the separate the folder for project number 1, for example. If you have project number 2, so you have another folder, because that is a good practice in programming. Because when you run, when you do programming, so when you compile your program later on, the compiler will generate many other files, the object file, the executable file, and so on. So you don't want to mix this file with other project, right? So the best way is to have one folder for one project. Okay, so you have this. This is the very important step where you need to choose the device that you use in your project. In this case, we use ARM Cortex M3, which is the microcontroller actually. Select this, click OK, and you will have this window, and you need to do some of the setting. So here is CMSIS. This is actually uh, the library that is used for the modern ARM development project. So we select this core, and in device select the startup, and we click OK here, and we will have the project navigation window here. And this is the this window that we can write our program. But before we can write the program, we need to create the program or the source file. You need to expand this, and here right click and add new item. So you will have this, and select ESM file, and give the file name. Add, and this is the space that you can run the or type your program. Okay, so let's have a very simple demonstration here. So to write assembly program for the ARM microprocessor, we need a header, what we call the direct instruction or assembler directive. In this case is this area. We need to use, this is not instruction set, we call it assembler directive, to tell the assembler the description of our program, our project. Area means we want to define the area that we save our program in the microprocessor memory, right? And the name of our project is PR 3021, and this is actually for code, and this is read only, and this is for linker, right? Although we export, although we use only assembly language, we need to have this linker directive. double underscore in and 3. So we write our program here. Our main program here. This is right. So for example, we want to move data into a memory, a 32-bit data. So we can use a move instruction, mov w, 32-bit, the first 32-bit, go to R0. So R0, and we use immediate data, and hexadecimal use 0 cross. Remember, in microprocessor, hexadecimal is you need to have this first, followed by the number 0 cross. For example, we have we want to have this in our microprocessor, for example, in R0. So this is our R0. So we want to have, for example, the data is 32-bit. So this is the first 16-bit, and this is the second 16-bit that we need to move into the R0. So the first one will go first. So we need to use mov w, and for this one to go, we need to use mov t. Okay, so back to this. So the first one is move w, 5, 6, 7, 8, and next one is we move mov t R0, 1, 2, 3, 4. Now we have the data in R0. Now, for example, we want to move this data to R1. So what is the instruction that we can use? So maybe we have the comment. Right, comment is very important in writing a program. This is for reference, for your reference, for your own reference, or maybe if you want to send this program to your friend or any other developer. So this will help other people to understand your program. Right? So this one is to transfer or move this number into R0, right? And next, you can have move. You want to move this value into R1. So this is the instruction, right? Move from R0, this is source, go to R1. Okay, so if we write this is move or transfer the content of R0 to R1. Now, let's, for example, we want to store the value, this data into a memory location, to this location, same location as this one, which is the, where is it? This 20000000. So we need to have the pointer that is point to that location. So we need to have another register. So in this case, maybe you can use R2, another register, R2, and here we have this value. So that is will point to the memory, this memory location, right? So we can again use move R2. The first value is 0 and have, right? So this one is the set pointer for R2 is pointed to memory address, this address. Okay, and now we can store the value. Now let's use the str store from art1. We send to what is pointed by R2. Okay, so this will demonstrate what we have learned just now, the move and the store, and for the simulation purpose we may need the NOP. NOP is no operation. Here later I will explain, and we will have a continuous loop here. This is just a continuous loop here after we finish on run the program here. This is necessary for microcontroller program, and at the end we have end. This is to end the program. So after we have all this instruction, so we can save the program by click this button, and we can compile. In this case it is called build. Build, right? So we can click this build button. So if your program is okay, so you will have 0 errors or 0, and also 0 warning. And sometimes you may get warning, depend on what is that warning. But if you get error, most of the time is because the data is not allowed, or you have the syntax error. Syntax error is easy to spot. For example, move t here, if you have something like move I like this, this is not the instruction, right? So when you compile, so you will have an error, and from that you can for example, look at what is this one is unknown opcode, MOVI. So you double click, the software will bring you to the line that you have the error. So this is wrong, so you change and you recompile, and so that you have no error. Or if, for example, you have the data is not correct, for example, the size of this is more than 16-bit, and you run, you have the error also. All right, so you see the immediate is out of range for this operation. So the value that that are allowed is within this range only, 16-bit, right? So, and again, you know already, oh, this is wrong. So you can edit your program and compile again, right? So after we compile, we can run the simulation to see what happens when we execute all these instructions, right? So to do simulation, we need to do some setting here. You need to right click here on the target one, right click, so you will get this window pop-up menu here, and select this option for target one. Click here this and go to debug and use simulator, and the other setting should be automatically like this. We just accept this, click OK, and now we can debug or run simulation. So click this debug button. So you will have this warning, evaluation mode. So this is because this software is the free version, so there is a limitation actually. So the size means that the size of your code, your program, is limited to 32 kilobyte only. Yes, and the program is very small here, so no problem for this case. So if your program is big, more than 32K, so you need a paid version of this software, right? So click OK. So this will be the debug window where we can access, or we can see the what is inside the microprocessor here, the core, right? R0, R1 until R15, PC, LRSP, everything. Initially we have 0, 32-bit, and we also have the condition flag here, XPSR. When we explain, expand, we have this negative Z, C, V, Q, and so on and so forth, right? So we can look at this. This is our code, and we have the startup. This is the startup that we select before this, and what we want to see is this. Okay, so we can look at the memory also. So to look at the memory, we can go to view, and we can go to memory window, and we can have up to 4 memory window view. So let's say we have one memory, memory view here. Here is the memory. So for example, we want to look at this address, this address. So these are the memory view. This is 1 byte 00, and this is the address, and this is the next address, which is 2000001. This is 2, 3, and so on until this is 2000030, and so on, right? So we will see. Maybe we change to this view like this. Okay, it's better. Now we want to run the program. We have this option to run at once, or to run to the certain part only, where we can use what we call a breakpoint. For example, we want to run the program until this part, so we can use breakpoint. So to get breakpoint, just bring your mouse to here and click to get this mark. This is the breakpoint. Or you can run using line by line. Run this line and see what happened. Run this line and see what happened. Or you can step over, means that you can skip some of the code, and you can have this option also, run to the cursor line. For example, if your cursor is here, when you click here, the microprocessor will run the program until this part. So let's, for example, we want to run our program until this, the first one. So we have our cursor here, all right, and we click this, and we can see that the first instruction is executed already here. This one is not run or is not executed yet, right? But this one run already, and what we have is that, see, 5 6 7 8 is moved to here already. R0 we have 5 6 7 8, and when we run the next one, maybe we can use this one, and here we can see, this is this assembly window, we call it. We can see our program. Where is our program now? This arrow, the yellow mark arrow, is point to the next instruction to be executed, all right, or the value of PC, all right. So you see the PC is the memory address that point that store your the next address to be executed, and this is the address in the memory that store the program actually, and this is your program instruction. And what is this? This is the machine code. Means that the mov w this is encoded to this value. This is 32 bit, you see, f2 4 5 6 0 7 8. So this is the encoding for this. Means that the machine code, the one that microprocessor understand, is this. This is the language, human programming language. But this one is the one that microprocessor know what to do. Okay, so when we click step in or F11, means that we want to run the next instruction, or this one, so we can run. So when we run this one, all right, we can see that, see, move top, this one is executed already, move top. So we have the all the 32 bit value in 1 2 3 4 5 6 7 8 in R0 now. And the next instruction is to move this, to move R0 to R1. So we expect that R1 we will have the same value as R0 when we execute this instruction. So let's do that. Right, see, now we have this already. R0 will go to R1. R0 will go to R1 when we execute this one. This one, this one, this one. Now we want to have this value in R2. So let's see, we expect R2 to have 20000000. Okay, run. So we have this, and now we want to run the last one, which is the str art1, means that we want to store this value into the memory location here. So let's do that. So see, when we run this in the memory, we have 1 2 3 4 5 6 7 8 in the memory. Okay, this value will go to the memory, and it is stored in the format of letter ending 1 2. So this will be the address of 20000003. This is 20000002, 20000001, and this one is 20000000. Right, all 32 bit will go to the memory. Okay, so that will be the demo of this. So you can try this. Right, so in the video that I shared with you last week, got tutorial on how to do this, so you can refer back to that video, or I will also share with you this recorded lecture, so you can try again to do this and to familiar with this software, right? Because this is very useful. And remember that our exam, our test is online, so you may need to use this software in order to answer your the exam question, right? So you need to know how to use this software, all right? And of course, you want to write the program, you need a computer, not on paper. You need a computer, need to write the program, need to execute, need to run the program and see what happened, right? That is the way to learn programming. Okay, so any question?
Doctor, I have a question, doctor.
Yes, please.
Doctor, for example, we want to move data to the address 20000000, like doctor did just now.
In, in
Uh,
in in the program, right?
yep, yep.
Uh-huh.
Since the value of the back four numbers are zero, can we straight away go to move t 2000?
Yeah, can. But yes, can. But this one we know, we assume that the initial value is zero. What if the initial value is not zero? All right, because sometimes the register is used in by our the startup program, yeah, the startup code. So before we run the code, actually there is a startup code that we attach in our program. So sometimes this is not initially not zero. So to make sure that it is zero, so better we do this.
Okay, doctor. Thank you, doctor.
Okay. Any other question? Okay. So if no question, we have a short break, 10 minutes, and before we come back and look at the next, huh? So we come back at 10 o'clock.
Okay, doctor.
Okay.